All right, get ready, because today we're diving deep into a theory that's causing quite a stir in physics. What if, and stick with me here, what if everything we think we know about gravity is, well, wrong?
It's a pretty bold claim, gotta admit, challenging one of the fundamental ideas of modern physics.
We're talking about the Grand Fibonacci SMF-RVS theory. Yeah, it's a mouthful, but stick with us. This theory says gravity isn't a pull from curved spacetime like Einstein said. It's a push created by, get this, magnetic fields and the vacuum of space.
Yeah, for like a century, Einstein's general relativity, that's been our go-to explanation. Massive objects warp spacetime. That's the idea.
Right, and that warping, that's what causes gravity.
Exactly. And the classic example, probably seen the pictures, is gravitational lensing. Light bending around galaxies, creating these distorted images. Pretty cool stuff.
Those space telescope images are incredible, always blows my mind. But hold on, if we're tossing out curved spacetime, how does this new theory, this SMF-RVS, how does it explain gravitational lensing? That's a pretty big deal to explain.
It's where things get really interesting. So the SMF-RVS, it stands for subtle magnetic fields and the relative vacuum of space. And it suggests the vacuum, well, it's not truly empty.
Okay, so there's something there.
There's varying pressure, and those subtle magnetic fields, those SMFs, they create even more pressure differences all throughout the universe.
So instead of a smooth sheet, space-time is more like what? A choppy sea of pressure? Okay, I can kind of picture that. But how does that bend light? Light's moving pretty fast.
Think of it like, imagine light going on a road trip across the cosmos.
Hmm,
In general relativity, the road itself is curved, right? That's gravity doing the curving.
makes sense.
But with SMF-RVS, the road, it's straight. The pressure along the way, that's what changes the traveler's path. Light gets pushed, redirected by these pressure gradients.
So these pressure changes, are they strong enough to deflect something as fast as light? How does that even work?
It's a great question, and it gets to how SMF-RVS actually explains gravity.
Hmm.
So the theory is these SMFs, they permeate the relative vacuum of space, that RVS part. And they're not just sitting still. They fluctuate, interact, create all these complex patterns of high and low pressure.
Okay, starting to see the picture.
And those pressure gradients, according to theory, that's what we feel is gravity. Light, traveling through these gradients, it's subtly pushed towards areas of lower pressure.
So light's like a sailboat catching the wind, but the wind is vacuum pressure shaped by magnetic fields.
More like currents in the ocean, really.
Right.
Light isn't blown by the pressure, but it's steered by it, the path of least resistance, That's what causes the bending of light, what we observe as gravitational lensing.
Gotcha. Okay, starting to get it. But this is still a huge shift from like what everyone learns about gravity. Are we saying Einstein was totally wrong?
Not necessarily. Einstein was brilliant, no doubt about that. His theory has passed a lot of tests,
Yeah.
but there are these cracks, Like general relativity, it needs things like dark matter and dark energy to explain certain things we see, but, well, we've never actually detected either of them.
Right. Those are still big mysteries.
And that's where SMF-RVS offers an alternative. Imagine the universe as this giant tapestry woven with these subtle magnetic fields. The variations in the weave, that's what creates the pressure differences, and those pressure differences, that's what we feel is gravity. No need for invisible matter or energy.
So it's a simpler explanation, more elegant maybe, but is it just a theory or is there actual evidence to support it? So there has to be a way to test this right, like some experiments that could prove or disprove SMF-RVS. What would those look like?
Yeah, definitely. So one of the big things SMF-RVS predicts is that gravitational lensing, it should actually change over time.
Hold on, really? It's not constant.
If those subtle magnetic fields are, dynamic, fluctuating like the theory says, then the lensing they create, well, that should vary too. Think of it like a ripple in a pond. It changes shape as it spreads out.
Right, ripples move and change.
Lensing patterns in space, they should kind of shift over time if SMF-RVS is right.
So we'd have to watch the same galaxy cluster for ages and see if the light bending behind it, if that actually changes.
Exactly. And astronomers are already doing this.
Wow, they are.
Tracking lensing patterns meticulously
Yep.
over years, decades even. If they find those variations, it would be, well, huge for SMF-RVS.
Okay, that's one way. What else?
Another prediction, and this would be really wild, is we might find strong lensing where there's no mass we can detect.
Wait, what? Lensing without any matter there.
Think about it. General relativity says lensing happens because mass warps spacetime. But in SMF-RVS, It's the pressure gradients causing the lensing, and those, well, they might not always be right next to a massive object.
So we could be looking at a totally empty spot in space and suddenly see light bending around it like there was a massive galaxy there.
It'd be pretty mind-blowing, right? It'd really point to something more going on with gravity than just, the curvature of space-time.
Okay, I can see how that would throw a wrench in things. And, earlier you mentioned SMFRVS could explain things general relativity struggles with, like how galaxies rotate. Can you break that down a bit more?
Sure. So one of the big puzzles in astronomy is that stars on the outer edges of galaxies, they orbit way faster than they should based on the visible matter.
Right, like there's not enough stuff there to explain how fast they're moving.
That's where the idea of dark matter came from. This invisible stuff making up most of the mass in the universe, but, we've never actually seen it.
Right, dark matter. It's a placeholder almost.
But SMF-RVS, it says we might not need dark matter at all. Those pressure gradients we talked about, they could explain those super fast rotation speeds.
So instead of a halo of dark matter around each galaxy, it's more like this pressure difference pushing those outer stars along.
Exactly. Those big galaxy-wide magnetic fields, they create pressure variations that affect how stars move within the galaxy. That could be what's causing those weird rotations we see.
I'm starting to see how this changes things, but man, it's a lot. Even the expansion of the universe. I mean, general relativity has trouble explaining that too, right?
You're right. To make their equations work, cosmologists had to introduce dark energy, which is, well, another mystery. This force pushing everything apart faster and faster.
Another placeholder, like dark matter. We know something's there, but we don't know what it is.
Yeah, exactly. But SMFRVS, remember, says the vacuum of space, it has varying pressure. And that pressure, it's not static. It can change over time and across massive distances.
So are you saying changes in that vacuum pressure that could be driving the expansion, not dark energy?
That's the core idea. It's radical, but it fits within SMFRVS.
My head's spinning a little bit. We've
Yeah.
gone from gravity to, like, the structure and evolution of the entire universe. And what about black holes? Those seem pretty important.
Right, well, in SMFRVS, black holes, they're still areas of super low vacuum pressure, but they're not those infinitely dense singularities like in general relativity.
Singularities. They always seemed a little, I don't know, too weird to be true. So if there's no singularity, what is there?
Think of them like incredibly powerful whirlpools. But instead of water, it's magnetic fields and vacuum pressure swirling around.
So a pressure vortex instead of a bottomless pit in space-time.
And because there's no singularity, there's also no event horizon. That point of no return.
Wait, so you're saying things could actually escape from a black hole in this theory?
Theoretically, yeah. The pressure and magnetic fields, it make it super hard, like swimming upstream against the strongest current ever. But not impossible.
So SMF-RVS, it's changing everything about black holes, too.
It's definitely painting a very different picture. One that fits with the idea of pressure gradients and magnetic fields shaping everything.
This is all mind-blowing stuff. But what does it mean for us? If this is right, I mean, how does it change our understanding of the universe, our place in it? I feel like we've jumped down the rabbit hole with this one. If SMF-RVS is right, it changes, well, everything.
It definitely shakes things up, that's for sure. But that's science, right? Always discovering, always revising what we thought we knew. Who knows, maybe in 100 years, SMF-RVS will be the accepted theory, and someone will come along with an even crazier idea.
You're right. We can't get too attached to any one theory. Always more to learn. For our listener, though, who's maybe hearing about SMF-RVS for the first time, what's the big thing they should take away from all this?
I think the biggest takeaway is don't be afraid to question what we think we know. For ages, everyone thought the Earth was flat. Seemed obvious, right? But new evidence popped up, new ways of thinking, and bam, our whole view of the world changed. SMF-RVS, it's like the reminder, even the most basic stuff in physics, like gravity, we can reinterpret it as we get more data, better tools.
So it's not about memorizing every detail of this theory, but about being open to new ideas, even if they sound strange at first.
Exactly. Science is a journey, not a destination, And sometimes the most unexpected detours lead to the most amazing discoveries. Even if SMF-RVS isn't the final answer about gravity, just exploring it, it helps us understand the universe better, makes us think in new ways.
It's like we've been given a new set of glasses to look at the universe with. And even if they need some tweaking, we're seeing things we never could have imagined before.
Love that analogy. And who knows what other mind-blowing theories are out there waiting? What other assumptions are we taking for granted that could be totally wrong? That's the beauty of it all. There's always more to explore, always deeper to go.
Well, this deep dive has been quite the ride. We started with curved space-time, something we thought was settled science, and now here we are talking about gravity as a push caused by, what was it, subtle magnetic fields and vacuum pressure.
And we've seen how SMF-RVS could explain those tricky things like gravitational lensing, the way galaxies spin, even the expansion of the universe, and
Yeah.
yeah, even black holes.
Some seriously wild concepts. The vacuum of space having pressure, these magnetic fields weaving through everything, creating those pressure differences, those gradients. It's almost like a whole new language for describing how the universe works.
It is. And even if some of the finer points of SMF-RDS get revised, the main thing, the questioning, the exploring, that's what pushes science forward.
That spirit of always asking why, that's what got us from thinking Earth was the center of everything to knowing about this vast, expanding cosmos.
And who knows what incredible things we'll discover next.
Well, on that note, I think it's time to wrap up this deep dive. We've given our listener a lot to think about.
We definitely have. If it sparks some curiosity, a desire to learn more about the universe and all its mysteries, then mission accomplished, I'd say.
So, as we sign off, one last thought.
Hmm.
The universe is an amazing place, full of secrets just waiting to be found. Don't be afraid to question, to explore, to imagine. The next big discovery could be right around the corner. And it just might change everything.